let's go ahead and evaluate a triple integral for an explicitly given function. So this is already in iterated integral form. We don't have to go ahead and define our region to make that happen. And I went ahead and wrote the answer out for myself so that I have a good self-check without having to reference documentation. So we're here. What we notice is we have something in terms of x, y, and z, which we expected. And we're integrating first with respect to z, which makes sense because our limits are in terms of both x and y here. Our limits are only in terms of x, so that makes sense that we're going to integrate next in y. And these limits are just constants, which is for x. So this is what we expect. So let's go ahead and kind of get started. The way we do this is very similar to the way we've done double integrals. We just now have an extra piece. So if I want to take the antiderivative of this with respect to z, well, I can think about a few things. One is that everything else in here is constant except for this. So let's go ahead and write that out to say that's 0 to 2, 0 to x, 0 to x plus y, e to the x times y plus e to the x times 2z. So let's pull that out. Let's say that's 2e to the x z. So again, this is constant. So the antiderivative here, if this was 4, the antiderivative would be 4z. So the antiderivative of this is e to the x times y z. 0 to 2, 0 to x, e to the x, y, z, and the antiderivative, so this is constant, so we add 1 to the power of z, and then divide by that power, so the 2's will cancel. So now I have e to the x, z squared, from 0 to x plus y, dy dx. So when I plug in 0, these are going to go away. And what I notice is that e to the x is common to both of them. So what I have is 0 to 2, 0 to x, e to the x, y times x plus y squared dy dx. So if we go ahead and multiply all of this out, we get 0 to 2, 0 to x, e to the x. So look, we get what? xy, we get 2xy here, so we get 3xy, and then we get y squared, so 2y squared plus x squared dy dx. Now, this e to the x is actually constant in this integral as well, so I can pull it out all the way here. So I get 0 to 2 e to the x times 0 to x of 3xy plus 2y squared plus x squared dy dx. Okay? So this is not constant. This is not constant. That is constant. So we could do some shifting and pull some stuff out, but let's not do that. Let's just go ahead and get antiderivatives here. 0 to 2, e to the x. So that's going to be 3/2 xy squared plus 2/3 y cubed plus x squared y from 0 to x dx. So when y is 0, all of these three evaporate, but when it's x, I get 3/2 y cubed plus x cubed plus 2/3 x cubed plus x cubed dx. So let's bring all this into one thing. So 3/2 is 9/6 plus 4/6 plus 6/6 equals 19/6. So now we have 19/6 x cubed e to the x dx. Okay, so x cubed e to the x dx. There's a couple ways we could do this. One is to use a table, right? There's tables for x to a power times e to the x. Simple, easy peasy. I think usually it's x to a power e to the alpha x is a lot of times how you see it. But I'm going to show you a trick. The second way to do this is by integration by parts. And that's also perfectly fine to do. But there's a third way that if it's just e to the x, I don't think this works if it's e to the anything but e to the x. But there's a trick because of the way integration by parts has to work. You can, I'll just show you. So you start with this piece, you say x cubed e to the x, and then you subtract the derivative on x, 3x squared e to the x. All right, and so now instead of subtracting, we add, and you add 6x e to the x, and then you subtract 6 e to the x, and then you add 6, and then you're done. Wait, no. All right, give me just a second. The reason this works is because e to the x always takes its own derivative. So if you were taking the derivative here, you'd end up with the derivative with the product rule. The derivative of e to the x is just this. The derivative of x cubed is 3x squared. Okay, so then over here, the derivative of e to the x is just e to the x. So those the 3x squared term that this one generates with the derivative cancels with this one. The derivative of this is negative 6x, 0 over here. This derives to e to the, this derives to 6x e to the x. So that cancels that one. This goes to negative 6 e to the x. And then you're just done, right? There's no, because the derivative of negative 6 e to the x is just negative 6 e to the x. So this one doesn't generate two terms. All these generate two terms. Anyway, the trick is if you have something like this, you just kind of walk yourself down until you have no x's left, and then you're done with pluses and minuses. It's just kind of a neat trick you learn along the way. So that is this thing's integral, all the way from 0 to 2. So when this thing is 2, you end up with 8e squared minus 12e squared plus 12e squared minus 6e squared. When this thing is 0, that's 0, 0, 0, negative 6. So you have 19/6. Those cancel. That becomes 2e squared. That becomes positive 6. 2 and the 6 cancel to get 19/3. 6 is canceled to get 19. Lo and behold, we get the answer we're looking for, and that's a pretty simple introduction to how you do iterated integrals for triple integrals.